Hello everyone, my name is Bachir Khadir, and today I want to talk to you about learning dynamical systems with side information. Consider a continuous time autonomous dynamical system given by the equation x dot equals f of x. F here is a function from Rn to Rn and is called a vector field. In dimension 2, or when n equals 2, I can represent this vector field as a stream plot. The setting I am interested in is one where f is unknown to me, meaning that I don't see these arrows in the background. And my goal is to learn f on some compact set omega of interest from a bunch of trajectories. More specifically, I have access to some measurements of the state variables and their time derivatives. I'm going to assume that my measurements are scarce and noisy, so I need to exploit what I call side information. By side information, I mean any information you might have about the dynamical system in addition to the trajectory data. It could come from common sense, some domain-specific knowledge, laws of physics, etc. Whenever I bring up side information, I'm going to call on the side information guy, and his job is to give me the side information that I need one by one. Side information could be, for example, the knowledge that my system has an equilibrium point somewhere. It could be that I know of some set that is invariant with respect to my dynamical system. There is trajectories that start inside this set, stay in this set forever. It could be the knowledge of two sets A and B, such that trajectories starting from A always reach B or never reach B. It could be that I know the sign of the time derivatives of the state variables on some regions of the space, or it could be that I know that some components of my vector field are monotone on some regions of the space. So our approach is to fit a vector field to our data by solving a least squares problem, and I'm going to parameterize the candidate vector field as a polynomial, meaning that the entries of my candidate vector field are polynomial functions of the state variables of some degree, and the coefficients of these polynomials are the decision variables of my least squares problem. And now I need to impose the side information that the true and unknown vector field f satisfies on my candidate vector field p. So now I'm going to show you how to use SOS, or sum of squares techniques, to impose side information on candidate polynomial vector fields. Let's say that the side information I want to impose on my candidate vector field is that its first component, call it P1, should be non-negative on some set A, and let's say A is defined by some polynomial inequalities. As we will see later on in the numerical examples, imposing side information on a candidate vector field often boils down to imposing that some quantity associated with the vector field is non-negative on some given set. So the question is, how can we search efficiently over the space of polynomial functions that satisfy some non-negativity condition? Actually, let's take a step back and ask even a simpler question. Assume that P1 is completely known. Assume that I know all the coefficients of P1 exactly. How can I check that P is globally non-negative? That is, no matter what value of x I plug in inside of P1, I always get in a negative quantity. Well, this question is not as easy as it seems. In fact, testing whether a polynomial is non-negative of degree as low as 4 is known to be NP-hard. So here is the key insight. Assume that somehow I can write P1 as a sum of squares of other polynomials Qi. Then it becomes obvious that P1 is non-negative. And the nice thing about this sum of squares decomposition is that testing whether a polynomial is a sum of squares can be cast as a semi-definite program. In fact, even searching over the space of sum of squares polynomials can be done via a semi-definite program. Recall that a semi-definite program is the problem of optimizing a linear function over the intersection of the cone of positive semi-definite matrices with a hyperplane. Semi-definite programs can be solved to arbitrary accuracy in polynomial time using interior point methods, for example. So now, back to the original question, how can I impose during the learning phase that some polynomial, call it Q, is non-negative on some set A defined by a fixed set of polynomial inequalities. Here is the idea. If I can find some sum of squares polynomials sigma 0 to sigma m such that the following identity holds, then I have ensured that Q is non-negative on the set A. To see why that's true, take a point x in the set A, then every term that appears in this sum is non-negative because we're either looking at some sigma I of x, and sigma I is a sum of squares, so non-negative, or we're looking at some gi of x, which is non-negative because we took x to be inside the set A. The nice thing about this decomposition is that we can search for it using semi-definite programming whenever we bound the degrees of the sigma i's. Furthermore, thanks to Putiner's theorem, which is one of the deepest results in algebraic geometry, we know that such a decomposition always exists for non-negative polynomials on A under some mild assumptions. This is the end of the review. I'm going now to be as concrete as possible and walk you through some numerical examples. The first one is from epidemiology. The dynamical system I'm going to show you has appeared in the literature as a model for the spread of a sexually transmitted disease like gonorrhea in a heterosexual population. So here I have two state variables, x1 and x2. x1 represents the fraction of infected males, x2 represents the fraction of infected females. The dynamic for the time evolution of the fraction of infected males is as follows. So as you can see here, there are two terms. The first term is the recovery rate, so we're assuming here an exponential rate of recovery. And the second term is the infection rate. And as you can see, it's proportional to 1 minus x2, which is the fraction of males that are not infected yet, times x2, which is the fraction of females that are already infected and could potentially infect the males. There is a similar equation, of course, for the spread of the disease in the female population as well. So in summary, what I have is a vector field in dimension 2. So I can plot it for you. For the following values of the constants ai and bi, the stream plot of the vector field f looks like this. So now I'm going to assume that I do not know the value of these constants. Actually, I'm going to assume that I do not even know that f has this special structure. So I don't know what f is. I don't get to observe these arrows in the background. What I have access to is a single trajectory, or to be more precise, I have 20 noisy measurements on a single trajectory of this dynamical system, and from it, I'm going to try to recover this vector field f. If I fit a polynomial vector field of degree, let's say 3, to this data by solving the least squares problem I showed you earlier, you get a vector field that looks like this. Now, if you look closely, you can see that this vector field is trying to do the right thing close to the observed trajectory, but its behavior otherwise is really bad. So what can we do to improve that? Well, we can use side information. So what kind of side information can we come up with here? Okay, one thing we can say is that the origin should be an equilibrium point. And that's simply coming from the fact that if there is no male or no female that is already infected, then the disease cannot spread. And as you can see here, this side information is already satisfied by the true vector field, but is not satisfied by the vector field we just learned. So what we can do is add this as an additional linear constraint to our least squares problem and solve it again. And if we do that, we get the following stream plot. What other side information can we think of? Well, the side information guy is telling me that the unit box should be invariant. And this is simply coming from the fact that x1 and x2 represent fractions, and as such, they should be bounded at all times between 0 and 1. So how can you impose that a set is invariant during the learning phase? For simplicity, take a set that is defined by a single polynomial inequality. I want trajectories that start inside this set to never leave it. So how can I impose that? Well, I have to look at the times where my trajectory meets the boundary of the set. So in particular at those points, g of x should be equal to 0, And at those points, I should look at two vectors. The first vector is the gradient of g at that point, which is pointing at the direction of biggest increase of my function g. And the other direction I should be looking at is the direction that f is telling me to take. And now for my trajectory to be invariant, I need the inner product between these two vectors to be in a negative, because otherwise I would go outside of this set. As you can see, what I need to impose now is that some quantity that depends linearly on my vector field should be in a negative on some regions of the space defined by the polynomial equality g of x equals 0. And this is exactly the kind of constraints that sum of squares techniques can handle, so I can impose this condition via semi-definite programming. So I do exactly that, and I get the following vector field, and as you can see now, the arrows are pointing inside of the unit box. Let's consider a last side information. So here the side information guy is telling me monotonicity. And actually for me to explain this to you, it will be easier for me to tell you why the learned vector field does not satisfy this side information. So let's say I fix the number of infected males to 40%, okay? So I am on this vertical line. Now what I'm gonna do is I'm gonna track the rate of infection of males as I move up this vertical line. So if I'm here, there are almost no females infected in the population. My vector field is telling me that I should expect about 5 males to be infected every day. Now, if I increase the number of infected females in this population to here, the vector field is telling me that almost no male is infected anymore. And this simply does not make sense. If there are more females that carry the disease in my population, I should expect the rate of infection for males to increase, not to decrease. And this is not satisfied by this vector field that I just learned. So I need to impose this additional constraint explicitly. It is not very hard to see that this constraint is a negativity constraint on the partial derivative of the first component of my vector field. And there is a similar equation that I get by switching the roles of males and females in this explanation. And these are exactly the kind of constraints that can be enforced by the sum of squares techniques I showed you and via semi-definite programming. So by adding these additional constraints to my least squares problem, I get the following vector field. And as you can see now, we are starting to capture the right qualitative behavior of the true and unknown vector field, even though we have learned it just from 20 noisy measurements from a single trajectory. Let's now switch gears a little bit and talk about an optimal control application. Imagine now we are in the shoes of a policymaker and we have two decision variables at our disposal, U1 and U2. U1 represents the fraction of males that are tested for the disease every day, and U2 is the fraction of females that are tested for the disease every day. As you test more people, the spread of the disease is going to slow down. And let's imagine it slows down according to the following equation. But there is a cost to testing more people. More specifically, our final cost is the sum of the fractions of males and females that are infected by the disease at the end of some period of interest t, plus some monetary cost associated with testing people. In any case, what is important here is that if I know f exactly, I know exactly the shape of the cost surface, and I can pick U1 and U2 in such a way that minimizes this cost of interest. But now imagine that I do not know f, and I'm in the same setting as before, where I only get to observe 20 measurements of a single trajectory. So what I am going to do now is use the framework of learning with side information I just presented to you, and use the vector field I obtain as a surrogate or a proxy for the true vector field, and base my decision on that vector field. Let's see how well that does. If you simply solve a vanilla least squares problem, this is the decision you would be making, and as you can see, it has a prohibitively bad cost. And as you include more and more side information during the learning phase, you can see from here that the cost you get is getting better and better. In particular, this is the decision that you would be making by incorporating all of the side information I have showed you. And this is what the true minimum of this cost function looks like. And from here you can see that these two values, the two costs, are pretty close to each other. Let's now move on to a second example, this time from physics. This is the simple pendulum, and the dynamics is given by this second order differential equation. By a simple and classical trick, I can transform it to a first order ordinary differential equation, which lead to this two-dimensional dynamical system. Lucky for us, we're working in 2 dimensions, so I can draw here for you the stream plot of this vector field. Let's imagine now that this vector field is unknown to me, and the only thing I have access to is trajectory data. More specifically, I take my pendulum, put it in some initial condition, let it go, and I'm gonna track this trajectory, and I'm gonna make 5 noisy measurements. Then again, I'm gonna take the pendulum to a different initial condition, and I'm gonna let go, and I'm gonna make 5 noisy measurements on the trajectory again. So overall, I have 10 noisy measurements, and that's all I have. So let's think about what side information we can use here to help us with the task of learning. One obvious side information is symmetry. If I flip the pendulum around the vertical axis, the dynamics does not change at all. What this means for the vector field is that if I rotate it by an angle pi, I get back the original vector field I started with. As it turns out, this is a simple linear constraint that I can easily add to my least squares problem. The second side information is that gravity always pulls you down. This is something you might know without knowing exactly the expression of the gravitational force. What this means is that when theta is positive, your speed should decrease because gravity pulls you towards the origin. And when theta is negative, your speed should increase. The third side information is the fact that the system is Hamiltonian. And this is simply coming from the fact that there is no dissipation of energy through friction with air, for example. So this was the list of side information we are going to use. Let me now show you the added benefit of using this side information during the learning phase. If I fit a polynomial vector field of degree, let's say 5, by solving a least squares problem, I get this vector field here. Again, you can see that it kind of overfits to the noise in the trajectory data, and its behavior outside of the observed regions of the space is not correct. Let me now add the side information that I showed you one by one. So the arrows are going to move, and we're getting new solutions. And as you can see, the behavior of the learned vector field is getting better and better, even though we have learned it just from 10 noisy measurements. I'm going to end this talk by a theorem that justifies our choice for working with polynomial functions as candidate vector fields. You can think of this theorem as a density result, like Stonewar-Strass approximation theorem, for vector fields under constraints that come from the dynamical system world. Keep in mind that this is a simplified version of the theorem, and I invite you to take a look at our paper for the full statement of this theorem. The link will be provided at the end of this video. The theorem is as follows. For any vector field f that is continuously differentiable and defined on a compact set omega, for any time horizon that you care about, t, for any accuracy epsilon, if f satisfies any one of the following side information that I'm going to list now: equilibrium points, a symmetry condition, non-negativity of some components of the vector field, non-negativity of the partial derivatives of some components of the vector field, invariance of some given set under some condition, a gradient or Hamiltonian structure. Then there exists a polynomial vector field P, such that trajectories of f and p remain within epsilon distance of each other for all times t between 0 and capital T. And the polynomial vector field P satisfies the same side information constraint that f is known to satisfy. What if f does not satisfy just a single side information, but a combination of side information? Can I still get the guarantee that there exists such a polynomial vector field P? Well, in general, we prove that polynomials might fail to satisfy some specific combination of side information, But if we allow for some room of error, delta, and we can take delta as small as possible, as long as it's positive, then there exists a polynomial P that delta satisfies, not exactly satisfies, but delta satisfies any combination of side information you care about while staying close to the vector field F. And as a bonus, all such properties of the polynomial vector field P come with a sum of squares certificate, meaning that we can impose them during the learning phase by semi-definite programming. Thank you so much for watching. I hope you enjoyed the video. Here is a link to the paper, and here is a link to my website.